morning, and today we're going to talk about something known as phase diagrams. I'm going to try and make this a short lesson because we have a shortened class period today. But phase diagrams, it's really just showing relationships of pressure and temperatures because we're talking about gases now, and those are the things that can the phase that can easily be compressed. So we just want to think about how things change when we change the pressures and temperatures. It's possible that sometimes you might also see these listed as being butt diagrams. I'll let you use your imagination as to why that is. But they are phase diagrams. We are just looking at the relationship of pressure and temperature. So the notes that you have in front of you, we're going to kind of fill those in a little bit later. So if you just want to follow along up here, first of all, we see that these are just diagrams that show relationships between pressure and temperature. And these diagrams are specific to that pure substance. So you might have a phase diagram for CO2, for H2O, for NH3. There's all sorts of different phase diagrams that would be unique to that pure substance, that compound. If we were to think about how this works, if you think, I'll start with the extreme here. If we have a phase that is at very low temperatures but very high pressures, what phase exists at low temperatures but high pressures? Solids. And then let's go to the other extreme there. What about really high temperatures and low pressures? What phase would you expect that to be? Gases. And then liquids are right in here. So that's what we're going to see with these phase diagrams. And there are all sorts of different points and some different things that we can see from this. Let me just ask you this. I know we haven't really talked about this word. Subliming, it just means turning directly from a solid to a gas. So can you guys think of any substance that turns directly from a solid to a gas in the pressures that we're used to being around at 1 atmosphere? Say it. Carbon dioxide. So dry ice, that's something that most people have played with at some point. And you see it going from that solid to a vapor. So it happens at standard pressures and the temperatures that we're at as well. So this happens to be a phase diagram for CO2, which is your dry ice. And there's a couple points about this, but I'm going to wait until we get to the diagram that you guys have in front of you to talk about it. Sublimation is turning directly from a solid to a gas. In other words, it doesn't go through the liquid phase. It just goes solid to gas. Okay, so another thing that once we get to the point to where we start writing down on our notes, don't worry about filling things in too much yet. We're going to talk something about the boiling points and freezing points and things like that. And we need to think about the pressures that they exist at during that time. Well, if I were to, and this is something on your notes, but we can fill it in a minute. If we're talking about going from a solid directly to a gas, what we just said is that that's sublimation. If you're going directly from a gas to a solid, that's known as something called deposition. We don't see a whole lot of this going on with substances because we don't exist at these low temperatures and these low pressures around these substances. So we're usually at a much different pressure, and typically temperatures that we're around would be somewhere in here. So we don't typically see a whole lot of deposition and sublimation of substances. If you have anything along this line, when you have a solid going to a liquid, that's going to be melting. When you have a liquid that turns to a solid, that's known as freezing. And then finally, along this line, what we see is that anything that turns a liquid to a gas, that's going to be vaporization, and if it's a gas turning to a liquid, that's known as condensation. Well, we can also, anywhere along that line, that's when condensation, vaporization occurs. But if the question is, hey, what about at 1 atmosphere? In other words, your standard pressures. So your standard pressure, that's known as your standard boiling point or standard condensating point. So for H2O, if that's what this is a diagram for, what temperature would you expect that to be at? 100 degrees Celsius. And your standard, in other words, at this unique pressure of 1 atmosphere, your standard boiling point or freezing point, you would expect for H2O, you would expect it to be 0 degrees Celsius. So we oftentimes, just in our normal language, we don't use the word normal with it. We just say, hey, the boiling point of water is 100 degrees and the freezing point is 0 degrees. But what that means is at 1 atmosphere. So that's the normal boiling point, freezing point. So it can boil or freeze at other temperatures as well if you change that pressure. Okay, this is where we get to the point that you guys have in front of you. And let me see, I think I can, sorry, let's see what I can do here. Let's do a dual page and then full screen. Okay, so I know this is kind of hard to see on the video, but you have a paper right in front of you. So the first question, it says, in this phase diagram for water, what is being plotted on the X and Y axes? So just make sure you know that pressure is on your Y, temperature is on your X axis. And then the next few questions just refer to what we just mentioned. So all along the AB, it says, what does line AB represent? Well, that's going to be sublimation and deposition. So maybe sublimation / deposition is how you want to phrase that. Sublimation, deposition. And then it also says, well, explain this in terms of equilibrium. And all you just really need to understand is that all along that line, you have both of those processes happening simultaneously. Not only is your solid subliming, but your gas is also depositing at the same time. It's occurring in equilibrium. Both of those processes are occurring. Okay, next one. It asks what is occurring along the line BD. And BD is right here. So again, this is going to be when you have vaporizing and condensing. Vaporizing and condensing. And then the last one along BC is when you have melting and freezing. Melting and freezing. So what about right here at this point, point B? What phase do you have right there? All three of them. That's why it's called the triple point. So number 5, what is point B called? It's called the triple point. It's just when you have all three phases existing simultaneously. All three phases existing at the same point. They exist in equilibrium. Okay, so now a little bit of a trickier one is D, which is right up here. And this point is known as the critical point. And this is going to be when you have conditions, or let's just say a point above which distinct gas and liquid phases do not exist. So above that point, you will not have distinct gas and liquid phases. And again, that's not something that we typically see. Look at that high pressure. Look at that high temperature. So that's not something that in our daily situations that we usually see those types of points for most substances. Okay, and then just number 7 is asking about reading off points. So just make sure you understand how to read this phase diagram. The triple point is going to be at a temperature of 0.01 and a pressure of 0.611 kilopascals. It's given to us in kilopascals. And then this numbers 8 and 9 refer to those normal melting and boiling points again. So whenever it has that term normal in there, you need to think to yourself, look to your standard pressure. So there's your standard pressure, which is 101.325 kilopascals. So your normal the first one? Normal melting point. So that's going to be right here. You just come till you hit that line, and you come on down and read it off. We would expect the normal melting point of H2O to be at 0 degrees Celsius. Normal boiling point of H2O to be at 100 degrees Celsius. And this is true because number 10, 101.325 kilopascals is your standard pressure. So that's why that works. Standard pressure. Okay, and then the last one, it says, is the slope of the solid-liquid equilibrium line BC positive or negative, and what does this tell us about water? Okay, so what we want to do here, there's this line right here that tells us a little bit of information. Water is pretty unique in this fact. If you look at that, would you say that that's a positive or a negative slope? Negative slope. So it's going to be negative. What does that tell us? Well, if you guys think about really what we're looking at is that interface between our solid and our liquid. Think about what you know with water. Water, H2O, is one of those really unique substances that is less dense in the solid phase. Your ice cubes float, right? So it means H2O is less dense as less dense in solid phase. And maybe you want to expand upon that. More dense in liquid phase. So most phase diagrams that you look at are not going to have a negative slope right there. Most of them will have a positive slope. And I'm going to jump ahead. Let me see if I can get out of this double screen. Okay, so let me just jump ahead to this right here. We've got carbon dioxide and H2O. So if we look at that interface and think about the slope, this is what most substances look like. I'm going to exaggerate it. There's a positive slope between your solid and liquid. So when you look at that and you take a straight line up, that arrow is going to point to the more dense phase. So your carbon dioxide, dry ice, is more dense than liquid. Solid dry ice, solid CO2, is more dense than liquid CO2. But it is not the case with H2O. It is actually that your liquid is more dense than your solid. All right, I think that's about it. That should do it for phase diagrams.